Alright, okay, so let's start. Alright, so the first topic I'm going to cover is about derivatives. Right? I mean, I expect you know about basics about calculus already, so let's talk about derivatives. So, what is a derivative? Well, a derivative can be thought as a rate of change for starters. So, by definition, I'm going to write definition here. By definition, we can say that dy dx, right, is equals to the limit as some delta x suddenly approaches 0 of delta y over delta x, which by quotient difference we can say is the limit as del x tends to 0, right, f of x plus delta x minus f of x over delta x, right? So you can think of it like this. First, let's look at this term here. Okay? This term here is the shift, right? We shifted from, so what did we shift from? Well, here we shifted from x to x plus delta x, right? For infinitely small delta x, right? So this here is infinitely small. Small, right? And then we subtract the shifted function. We call this a shifted function. So f of x plus delta x is the shifted function minus the original function, right? This here, right? Here is the original function. And we call this y is equals to f of x, right? Over the shift of delta x, right? So over change of delta x. So in mathematics, or at least in calculus, we call this the quotient difference. And the quotient difference says, is basically this, that the derivative irrespective to the derivative is equals to the limit as some del x tends to 0 over f of x plus delta x minus f of x over delta x. And for simpler purposes, I'm going to let h be delta x. Let h be delta x, such that we get this limit as h tends to 0 f of x plus h minus f of x over h. Okay? So let me give you an example of how to compute a derivative. Okay, so using a quotient difference. So here's an example. Suppose, and by doing this example, we're going to do I'm going to introduce you to another thing. So let's say we have to compute, right? Let's say we have to compute the derivative of y equals e to the x, right? E to the x is the exponential function, and using the quotient difference. So, so where do we start? Well, we start with this. We say we have to find f of x plus h, right? F of x plus h is e to the x plus h, right? F of x, right, which is y in this case, is just e to the x, right? Right. So what happens is we call the limit definition, or the quotient difference. So we say limit as h tends to 0, right, of e to the x plus h. So e to the x plus h minus e to the x over h, right? Well, remember that, here I'm going to write this in light green. Remember that e to the ab, right, it's the same thing as e to the e to the b. No. E to the a plus b is equals to e to the a, e to the b. That's my mistake, sorry. So if we remember this rule here, right, from I don't know where, we can rewrite this as limit as h tends to 0, right, e to the x, e to the h, right, minus e to the x over what? Over h, right? And if you look at this, we can carefully see that we can factor out an e to the x because we have e to the x on both sides. So we have this limit as h tends to 0, right, e to the x times e to the h minus 1, right, over h. Because I said I think you already know about calculus already, I'm gonna use a trick that is only learned in Calc 2, pretty much. So here, because e to the x is a constant, because look, e to the x is a constant, the reason is h is approaching 0, right? So e to the, so this can be rewritten as what? E to the x, right, times the limit as h tends to 0, right, of e to the h minus 1 over h. Suppose we don't know what the derivative of e to the x, e to the h is. It's e to the h if we take the derivative with respect to h, but suppose we didn't know that. If we just plug in 0, it's going to be 0. Okay, that doesn't work. Clearly doesn't work. But we can recall the Maclaurin theory expansion, or the Taylor theory expansion centered at 0. So recall, right? Recall e to the h, right, can be some as is equals to some as some k goes to 0 to infinity, right, of e to the of h to the kth power over k factorial. Okay? Alright, so let's recall this. What does this mean? Well, the sigma means is you start from k, right? You start from k equals 0, and you expand it up to infinity. So if we expand the first few terms of this Taylor series, right? So we said e to the h, right, is equals to some k equals to 0 to infinity of h to the kth power over k factorial, right? Right, so if we say this, right, let's plug in 0 to h, right? We get h to the 0, right, over 0 factorial, plus h1, right, over 1 factorial, plus h2 over 2 factorial, and etc. Right? So what do we get? Well, simply, h0 is 1, 0 factorial is 1, right? 1 plus h, right? I mean, h1 over 1 factorial, that's pretty obvious. Plus 1 over 2 factorial is 2 times 1, so it's 1 half h squared and etc., right? So let us plug in this expansion to this function over here, e to the h, right? So let's do this. So let's expand this. So e to the x, right, times the limit as h tends to 0, right? One plus h plus 1/2 h squared, right? Right? Minus 1 over h, right? Doing the mathematics, 1 eliminates, right? And what do we have? We have is e to the x, right? The limit as h tends to 0, right? Of h plus 1/2 h squared over h. Alright? So if we have h plus 1/2 h squared plus over h, right, we can rewrite this as what? E to the x. We can eliminate h, and this just becomes an h, right? We can eliminate h, and what do we get? We get is we eliminate h and we get this this. So limit as h tends to 0 of 1, right, plus 1/2 h. And if you plug in the limit, this 1/2 h becomes 0, right? And this is therefore e to the x, right? So we can prove, literally saying that the derivative of an exponential function is the exponential function itself, right? We can prove this, right? I mean, and yes, you have to memorize these kind of things. I mean, you have to memorize this. So let's try another one. Let's try another one. For example, I'm sure you know the basics of integration already too. So if we can do this with the derivative, we can do a similar example with an integral. For example, we can prove using Taylor series that the integral of e to the x is e to the x plus c. So let's prove that the integral of the derivative of e to the x dx is equals to e to the x itself. Okay? Plus a constant, but let's ignore the constant. It's equivalent to e to the x. Okay, never mind. It's equivalent to e to the x. Okay, so let's do this. So well, we said e to the x, right, is equals to 1 plus x plus 1 over 2 factorial x squared and etc. Right? By Taylor series, right? We proved this, right? We know that we assume that this is true. We didn't prove it yet, but we assumed that this was true. So let's do this. Well, suppose we take the derivative of this function. Suppose we take the derivative of e to the x, right? Then what do we get? 1, right? Plus the derivative of x is 1, right? So this here becomes here, right? Plus x. And if we had a third term, right? If we had a third term, suppose the third term is going to be 1 over 3 factorial x cubed, right? And etc., right? 3 factorial 6, right? So it's going to be 1/2 plus 1/2 x squared, right? Right, so and so on, right? And so on, right? So if you integrate the derivative, or if you integrate e to the x, right? If you integrate the derivative of e to the x, right? What do we get? We get x, right? Back plus 1/2 x squared, right? Plus 1/2 times 1/3 x cubed, and etc., right? So what is this? This is really the same thing as x plus 1/2 x squared plus 1/6 x cubed, right? And realize that it's just a Taylor series without the 1. X, right? I mean, look at this. We have x here. We have an x here. We have a 1 over 2 factorial x squared here. We have this here. And we have this here. And this here, right? And also note that the integral of the derivative of e to the x, dx is really just e to the x. dx, right? So we can also prove just using Taylor series that the integral of e to the x dx is e to the x plus a constant c. Right? I mean, it's a super interesting fact, right? I mean, so basically in this lecture, I kind of introduced you to applying Taylor series to integrate integrals and basic integrals and derivatives. And in the next part of this video, I'm going to introduce you to more about Taylor series and more about the definition of a derivative, if you know what I mean, and how we get this. So, see you next time. Thanks for watching.